We are now going to start creating a real model of production and use that as the basis for a model of economic growth. And we'll proceed step by step. The model will be a classical model with standard assumptions, the type of assumptions that you should be familiar with from microeconomics. The big picture is that this model is really just a classic production function equation. There's no investment in this model, which means that fundamentally this model is static. It's a static model, but we're going to interpret it in a way that helps us think about economic growth. By the way, when faced with the math in an economic model, it's important to understand the intuition, because really an economic model is just a story about human behavior, except that it's told with math and not so much with words. If you understand the story, if you understand the intuition behind the formulas, it will make it a lot easier to understand and work with the model. Now, the philosophy behind this model is that if we're trying to explain GDP levels per capita between nations, that is why nations are rich or poor, there are three factors. One is technology, one is capital inputs, and one is labor inputs. So the whole foundation of this model is that technology, capital, and labor explain why a country has the per capita GDP that it does have. So here's the little world that we are going to be working with. First, the only thing that gets produced and consumed is ice cream. There are no other goods or services. Ice cream is produced by a static population of workers. There's no population growth. Each one of the workers is the owner of their own little business, just like a farmer who owns their farm. Workers need machines to make the ice cream. They work with a certain level of technology. They sell ice cream to each other at a market price, and the revenue that each firm earns will exactly equal costs. Every business is identical to all the others. Workers and machines are all identical. When you set it up this way, really the economy is just a scaled up version of a single business. If you understand how a single business works, you right away understand how this economy works. Finally, there's no money in this economy. There are no dollars. Any payment is in the form of units of ice cream. And the textbook expresses that by saying ice cream is the numeraire, which is just a fancy French way of saying ice cream is not just the produced good, it's also the form of money, the medium of exchange. In this model, the workers actually wear three hats. They actually perform three different roles. When they are wearing their worker hat, they act like workers and they're working for a wage. When they wear their capital owner hat, they are renting out capital that is machines, for money. Now the money here is ice cream, remember. Thirdly, when they're wearing their business owner hat, they are figuring out how to combine capital and labor in the best way possible to produce ice cream and how to maximize profit. And the best analogy, the really good analogy is, imagine a farmer who owns their farm and who pays themselves a wage according to their own work on the farm, and they pay themselves a rental for the use of farm machinery which actually they own. And after you subtract costs from revenue, anything left is called their profit. So here's the basic equation for production. Total production and output, Y, is a function of two variables, K and L, capital and labor, machines and labor input. And we assume a specific form for the equation that gives us Y. The form of the equation is a technology parameter that doesn't change, that's why there's a bar, multiplied by K to the power 1/3 multiplied by L to the power 2/3. Now this type of equation is called a Cobb-Douglas production function. It's Cobb-Douglas because you have the two factors K and L, each raised to an exponent. In the case of K, it's 1/3. In the case of L, it's 2/3. And an important thing is that the two components, 1/3 and 2/3, when you add them together equal 1. That's not an accident that it's 1/3 and 2/3. It's got to be two fractions which, when added together, would equal the number 1. That's a Cobb-Douglas production function. Now, why do we assume this exact form? Well, this exact form has several nice properties, as we would say. The properties you will soon find out. One of the properties of this sort of function is that it has what's called constant returns to scale. Constant returns to scale intuitively mean if I take a single business with a single worker and whatever amount of machinery they're using together, and I increase capital and labor by the same proportion, like I double them, then output will automatically double as well. So double the inputs, you get double the outputs. Increase the inputs by a factor of 10, output will go up by 10. That's constant returns to scale. And because of this form of the equation, if I scale up an individual business, I actually get the whole economy. The whole economy is just a multiplied version of what's going on at the level of the individual business. Now, there are reasons why that's important. I won't say much about it, except that constant returns to scale mean that whether the economy is small size or medium size or big size, all of the equations we use still work. The equations work for a single business. The equations work exactly the same way if they're for the whole economy. So, Cobb-Douglas production function, we're assuming it. It gives us certain nice properties. This is an equation that tells us the motivation of the business owner. The motivation of the business owner is to maximize profit. Profit uses the symbol pi there, the max pi. you see max pi with K and L below. That means K and L are the two variables that the business is able to manipulate and change and choose in order to get the maximum possible profit. Now, the way we measure profit is we take total output from the firm, which is generated by F of K, L, and we subtract off the costs of production. The costs of production are the amount of capital you use multiplied by the rental cost of capital, and also minus the labor force multiplied by the wage rate. If you're wondering why there isn't a P in front of that FKL, why don't we have the price of the good, price times output, when we're talking about revenue? The reason we don't need a P is because everything is measured in ice cream, and ice cream is the numeraire, so the price of ice cream is 1. So it's 1 times FKL minus RK minus WL. Now this formula, FK, L, has certain properties when we create it and we make it into the version that we have, the Cobb-Douglas production function. That function has certain characteristics. One of the characteristics is that there is diminishing marginal productivity of labor. Diminishing marginal productivity of labor is a concept I will explain using an example. And the example I will use is a worker at Kaladi Brothers Coffee, which is what you see in the picture, working with a machine to roast coffee beans. So you've got one worker there, and he's working with a certain amount of machinery to roast beans. Now, think about this. The owners of Kaladi Brothers could improve the output of this single worker by giving him more machines to work with. If instead of one machine he had a second roasting machine and a third roasting machine, he could produce more coffee beans. But, as you can see there, if I give him a second machine to work with and a second bunch of coffee beans, he will produce more coffee beans, but the extra amount of coffee beans he produces will not be so much. His ability to utilize that second machine is a little bit less than his ability to fully use one machine. In fact, imagine keeping one worker there and you add more and more machines. You can see he's going to have to run between the different machines. He's going to have to empty in the beans to each one. He's going to have to move them around, spread them around like that. So, bottom line is, if we take this worker, he has one machine, and we give him a second machine, output will go up, but it's not going to double. It's going to go up by something, but it won't double. If we give this worker a third machine, output will go up, but it will go up by an even lesser amount. The idea being what we call diminishing marginal productivity of labor. Diminishing marginal productivity of labor means if you give a worker more and more machinery, eventually the extra benefit becomes less and less and less of getting that extra marginal machine. So now you have the intuition. This is the picture. The picture shows a single worker or a fixed number of workers. We really don't know. This could be for one worker, it could be 5 workers or 10 workers. It doesn't matter for the concept. The important thing is the number of workers, the value of L, is being held constant. And we start increasing the number of machines. that that fixed number of workers can work with. Output will go up, but it goes up at a diminishing rate. That's diminishing marginal product of capital. Now, one super picky little technical point here is that this graph extends all the way to the vertical line on the left where you have zero capital, and it's showing an output of 5 tons of ice cream. That zero capital point does not correspond correctly to the Cobb-Douglas production function. If you have a Cobb-Douglas production function and you have zero labor, it doesn't matter how many workers you have, you will get zero output. So at the very far left of this line, it doesn't apply to our model. You've got to have at least some positive amount of capital in the model that we are using. Okay, what's this equation about? Well, the textbook works through all of this, but when you play around with the equations, it turns out that the marginal product of labor, NPL, is equal to 2/3 times Y over L. That is to say, the marginal productivity of labor is equal to 2/3 of the amount of machinery per worker. And it's like saying, if you have a lot of output, if you're producing a lot of coffee beans with a small number of workers, a small L, then you have an imbalance in your operation. You've got a lot of machines but too few workers to use them effectively. So a lot of output, a big Y, a small L, means that there's a lot of potential benefit by adding one more worker. Think of our coffee roaster. What if he had 10 roasting machines and Kaladi Brothers was really cheap? They only wanted to pay for one worker. Well, they would be better off adding another worker or two. They would be better off increasing that L, because the marginal productivity of labor is very high. One more worker is worth a lot when there's going to be a lot of machinery for them to use. Now, I just said Kaladi Brothers will be a lot better off if they have a reasonable balance between the number of workers and the number of roasting machines. But that's a little vague. I have my one coffee roaster guy. I have a lot of machines. Sure, I know there's a benefit in hiring another worker to work with the many machines, but when should I stop adding workers? Should there be like one worker for every 2 machines? Or should there be one worker for every 1 roasting machine? At what point should Kaladi Brothers stop adding workers? Well, here's the answer. If you contemplate whether to add one more worker, you know what their marginal product is from the equation. You know how much extra output you'll get by adding one more worker. So what you do know is the benefit from adding one more worker in terms of extra units of coffee beans or ice cream in our original world, and using the market value of that extra coffee or extra ice cream, we can figure out what the point will be where extra value output will exactly balance out the wage we're going to have to pay the new worker. So if a new worker is going to add $100 worth of value every hour, then I should be hiring workers up to the point where I've reached my exact balance. I've hired exactly the right number of workers, no more, no less, according to the wage rate that's prevailing. Now, so far I've talked about the marginal productivity of labor. I've talked about how many workers you should have. You can flip this around exactly the opposite way and talk about marginal productivity of capital. Flip the example around. Imagine you have lots and lots and lots of workers but very few machines. Then if I add one more machine, I will get a bump in productivity. And that bump in productivity, that extra output from adding one more machine, is called the marginal product of capital, MPK. And in that case, if I'm starting with very few machines and I have a lot of workers, I should keep adding machines up to the point where the marginal productivity of capital, or marginal product of capital, equals the rental rate of capital, the rate I will have to pay to, in effect, rent that extra machine. Now at this point there's a little confusion, because why do we talk about renting capital? Don't firms buy capital? Well, it is confusing. What we're going to say is, just imagine that the way our business owner thinks about capital is a machine can work for them, or one of their machines can work for them, or one of their machines could be rented out to another firm. It's sort of like the same way that workers are paid by the hour. That's what the rental rate of capital is. Alright, at this point I sure hope you're following my notes and not just trying to follow my narration here, because I'm jumping over a lot of extra explanation that is in my notes and in the textbook, and there are more equations than what I'm showing you. I'm just giving you the big picture. Okay, so at this point, wait a minute. Where did the W and R come from? Who determines this wage rate and rental rate of capital? Well, in this little world, there isn't exactly a formal modeling of a labor market, and there isn't exactly a formal modeling of the market for capital. So we sort of assume there are these imaginary markets that we don't have to analyze, but though in those imaginary markets everything will get sorted out and capital will be valued at the appropriate rental rate, and workers will be evaluated at the appropriate wage rate. So these sort of labor market and capital market are behind the scenes. They're almost imaginary markets. Now, does this make sense to talk about an imaginary market without us trying to actually model it? Well, the whole model is imaginary, so there's nothing improper about imagining markets for factors of production along with everything else. Just assume we get equilibrium prices for inputs, and that these prices are what you would get if you went through the whole demand and supply modeling diagram analysis, like you see in the textbook with the diagrams there, which I am not going to reproduce. So in equilibrium, an equilibrium here means the solution where everything is appropriately valued and the right amount of output is produced with maximum efficiency. In equilibrium, the choices of firms and workers follow this rule about hiring up to the point where the wage rate or rental rate equals the extra product you get from hiring the extra worker or you're using an extra machine. There are these workers who, wearing their owner hat, will arrange their own work and other workers and the choice and number of machines to get maximum profit, maximum benefit. And once everything is worked out, it will all be a nice solution. And one thing about the nice solution is that when a firm earns revenue, they distribute the revenue partly to the workers, partly for the renting capital, and there's nothing left. Firms have zero ice cream profit remaining after they've paid for the cost of inputs. Now, this is not contradictory with the idea of maximization. Maximization of profit could mean zero profit. Zero profit is the best that you can do. And that's the case in this model. Now, I just asserted that profits will equal zero. That in equilibrium, when all the firms and all the factors are operating at maximum possible efficiency, there will be no leftover profit. Profit will be zero. How can I be so sure? The reason I can be sure is that it's a property that comes out of the Cobb-Douglas production function. And I refer you more to the textbook. But the reason we get this particular exact answer is because we chose the production function at the very beginning of the model, knowing that it would give us this result in the end. It's a property of the function that after everything is worked out, all the revenue from ice cream sales go to pay off labor and capital, and nothing is left as profit. So in this model, there's no such thing as a business owner who only owns a business and doesn't do anything else and yet makes money or makes ice cream. The only people who earn revenue, or the only people who are paid here, are the workers and the people who own capital, who are the same person, by the way, just like the farmer is simultaneously a farm worker and an owner of their own farm machinery. So there's no good news for someone who's a pure capitalist. You've either got to be a worker or you've got to be renting out machines. You've got to be in the machine owning business. So there is no stockholder here. There's nobody who is generating revenue from stock dividends, let's say. And that's what the equation says. The wage rate in equilibrium, that's what the little asterisk means, equilibrium value of wage, times the equilibrium value of labor plus the equilibrium value of the rental rate of capital times the equilibrium level of capital exactly equals equilibrium total output of ice cream. Nothing left over for anybody else. So here's the big picture solution story. In this model, there are 5 equations and there are 5 unknowns, 5 variables. So you play around with these 5 equations and you are able to solve for the equilibrium values of y, k, l, r, and w. And so you have solution values for each of those 5 things. And here they are. And the left-hand side are the variables we're trying to get the value for in equilibrium. The right-hand side are things we all know what all the values are, and you calculate in the way shown here. So this is the solution. Equilibrium means solution when you're doing modeling like this. Solution requires equilibrium, where everything is in balance. So what an economist would say is that in this model, in equilibrium, economic profit is zero. Economic profit is what is left over after you've made payments to all of the inputs. Now, why would this business even operate if economic profit is zero? Well, remember, these businesses are like farms, and when the farm is operating, the worker is the same person as the owner, and the owner is paying themselves a wage, and the owner of the business is also the person who owns the capital, and they're paying themselves a return on owning capital. So this is really a story similar to real-world small farms long ago. Farmers stay in business because they are effectively earning a wage by keeping the farm running, and they're effectively earning a return on being an owner of capital because they're paying themselves a rental. So zero economic profit is completely compatible with having a going concern, a business that continues to function. So what is the counterpart normal everyday word profit mean in terms of this model? Well, that kind of model, that kind of profit we call accounting profit. Accounting profit is profit or payment to the owners of capital who are renting capital to firms. Note, in this case, in this story, the owners of the capital are not like farmers. They're not like the people who are also working in the business. They're totally disconnected from the operation of the business. All they do is have capital, which they rent out. And that rent is called accounting profit. And if accounting profit was zero, nobody is going to lend their capital. Nobody is going to want to be in the business of making it possible to be in production. And the textbook explains this. Bottom line, economic profit and accounting profit are different concepts. Businesses can continue to operate even when economic profit is zero. So we have a model, and we want to test it against the real world. And so we have a table and also diagrams in the textbook that show the prediction and the reality from real world data. And I won't go through the whole table here with you. It's explained in the textbook where the deviation comes from. The essence, though, is that we're trying to test out this proposition that per capita GDP differences between countries are basically explained by technology, labor, and capital. That is, can a model that is based on the idea that production is generated by technology, capital, and labor, can it explain real-world differences in per capita GDP? Now, to simplify the test of the model, we'll make a drastic assumption. We'll assume that all countries have access to the same technology. So A is the same for everybody. And in fact, if it's the same for everybody, then we might as well set A to 1 and we do that by using the United States as the reference point. So once we set A to 1 for everybody, we've taken A out of the picture as a potential explanatory variable. We'll only be left with labor and capital now. And in fact, in the Cobb-Douglas production function model, if all you have is capital and labor, then it now becomes effectively capital per person that must explain production per person. It all comes down to that small k now, partly because we've taken technology out as a potential explanation, and partly because we have assumed this specific Cobb-Douglas model. So the text goes through everything here, and the bottom line is that no matter how you play around with the model predicts that most countries should be substantially richer than they are, and the poorer the country, the worse the prediction. And that's shown in graphs and explanation. So we end up at a point where we can explain some of the wealth of countries, but we find big gaps between prediction and reality, especially for poor countries. So we have a degree of ignorance about why growth is different between countries. So what we do in the final part of the chapter is adjust A for each country, keeping A equal to 1 for the United States, and we use that deviation of A away from 1 as a sort of indicator of our unexplained variables, the things outside capital per worker that are explaining GDP per capita. And we call this use of A the total factor productivity measure. Total factor productivity is really a measure of our ignorance about why this country's performance is so much worse than what we thought it should be with the model. So we can speculate what elements are captured under TFP, the things that we're missing out from our explanation. One of them is human capital differences. In our model, all workers are the same everywhere. They're identical. They're like clones. There's no such thing as a better educated worker. So maybe we're not capturing that. Maybe richer countries have better educated workers. Perhaps that's what we don't have in the model. Another possibility is really technology is not the same for every country. Every country doesn't have access to all of the know-how and all of the technological expertise that the United States has. So maybe those technology differences are the reason the model is inadequate. And finally, maybe institutions are different between countries. Maybe the reason for difference is government policies, rules, and regulations. In macroeconomics, the word institutions does not mean organizations. Institutions mean like the rules of the game, rule of law, stuff like that. So maybe some countries are just really badly managed, really badly run. Maybe there's no law, maybe there's no law protecting the property of the business owner, stuff like that. So those are three things that we could be missing out from this simple production model that explains why we can't predict who's rich and who's poor very accurately. So the text goes into this in more detail. The text also talks about the famous North Korea-South Korea natural experiment. There are other examples like what was East Germany and West Germany. We will come back to study the causes of growth again. But before we do that, we're going to create a model that you will be happy to hear is based on the model we just did. But the model we're going to talk about is by its very nature dynamic. It's going to be a dynamic model because we will allow for investment. Investment is the creation of new capital. So that makes the model dynamic, no longer static. And the model is called the solar model. That's the next topic, the next chapter, the solar model. So that's a lot of theory, a lot of equations. See you next time.